Hello my dears, how are you all? So what we studied in the last class, we studied about the DC motors, right? DC motor. And yesterday overall I gave an idea about the working of DC motor, and later I thought it's not enough. Okay, it's not enough. Later I thought actually for examination it won't be asked how it work and all, it won't ask, but we have to know what is the exact working of DC motor. I simply told in a magnetic field the conductor will rotate in a, so I want to explain more. Okay, then only it will be for my satisfaction, at least for my satisfaction. I want to tell you how the motor, DC motor exactly work. Okay, so for that let's take a heading like DC motor working. Okay my dear, okay my dears, DC motor working. So listen, simply consist it won't work now. Simply you take it like this. Simply you take it like this. Okay. Okay. Listen my dears, I will explain how a DC motor is working actually. See, a DC motor as well as DC generator, for converting AC to DC we require split ring commutator. These are the split ring commutators. Split ring commutators. Okay, the purpose of this split ring commutator is in order to convert the alternating current to DC or DC to AC. Okay, so we are giving a DC supply so that it come here, and through these brushes, these are the brushes my dears, these are the brushes, these are the brushes. So through these brushes it goes to the commutator segment 1. This is called the commutator segment. What? There are two segments. You assume there are only two segments. So one segment and the other segment. It come to the one segment and is come here and come to here and come here like this, and it move upward, and like this it will come here, and it will return path, it will come like this. So in the coil side, suppose you consider a single coil, so this will be the single coil structure. So in the single coil, in this side the current will be in upward direction, and this side the current will be in downward direction, and the temporary magnet allows a flux from this north pole to south pole, and it is continuously flowing, and it's continuously cut the conductors, right? This continuously cut the conductor. Okay, so what happened by using Fleming's left hand rule? Fleming's left hand rule, it is also called motor rule. Motor rule. So by using Fleming's left hand rule, what Fleming's left hand rule says is that take your left hand and arrange your fingers, I mean forefinger, middle finger, forefinger, middle finger and thumb in mutually perpendicular direction like this. See, like this, mutually perpendicular direction, and the thumb will represent the direction of the force, and the forefinger will represent the direction of the magnetic field, and the middle finger represent the direction of the current. That is the what Fleming's left hand rule. This rule is applicable to, or this based on this rule the motor is working, DC motor is working. So let us apply that rule here. So the field lines is from what my dears? From north to south. Okay, this is exactly correct along with my field direction. And see, the current is from what? This is force, this is field lines, and this is current. So the current is current here. See, this is the current. So what happened? This is the current now. So this is the current direction. So the current is downward. Okay, the current is downward direction. And what will be the force here? The force will be towards this direction now. So towards this direction. Okay, is it clear? So what happened? There will be a force on this side of the what? Conductor, and this force will trying to move this conductor side towards me. Am I correct? See, this is the field direction north to south, and this is the current direction. Correct, in that direction also the current is flowing, and this will be the force. So there will be a force acting towards me from the board now. So this side will exert a force like this, and it will move like this. So this region will try to move like this, and say the opposite side, what will be? See the opposite side. So same Fleming's left hand rule I can apply here also. What happened, my dears? The current will be from the force is from north to south now, the field poles. So the flux lines is from north to south, so it will be same, and the current is towards what, my dear? Towards this direction. See, so what happened? What happened to my, this is the direction now, so mutually perpendicular means yes, this will be. So what happened? This side of the coil now, this side of the coil, it will exert, or it will be exerted by a force which is acting to move towards it inside, towards the inside of the board. So here it is away from the board, here it is inside the board. What happened? There will be an effective turning effect, and the coil start rotating. And what happened when it is come here, and exactly perpendicular direction towards me? It is exactly perpendicular means what happened? There will not be any flux lines linking. There will not be any lines of force linking. So what happened? The torque will be zero. The torque will be zero, because the angle, there is angle between torque NABI sin theta. Now I already explained now. Torque is equal to what, my dear? NABI sin theta, where theta is the angle between what? A line perpendicular to the surface of the coil and the lines of force. So theta will be maximum when this is in this position. So this will be theta. The line surface, I mean the angle between the line surface to the perpendicular to the surface of the coil. So this is the line and the lines of force, my dear. So what will be theta now? Theta will be now 90 degree. So this is flux line direction, this is the perpendicular direction. So this position only torque will be maximum. When come to here and come to here and come to here, what happened? The torque will be 0. So the coil will try to stop by itself. The coil will try to stop by itself. So in order to reduce that problem, because we have to continuously rotate the motor now, we have to continuously rotate the motor. So in order to reduce that problem, what we are going to do, we are mutually placing another coil which is perpendicular to the first coil. That means suppose single coil is like this, another coil is placed like this. So it will be mutually perpendicular to first coil. So what happens, whenever there is one side 0 happens, I mean when moving the rotation, during the rotation the 0 happens, the other coil will face in the perpendicular condition. So there will be a uniform torque and that there will be a continuous rotation. There will be a continuous rotation. Is it clear? So that is the simple working of the DC motor, my dear. Okay. So that's all. Actually, I simply told you now yesterday, there will be a turning rod for force and it will rotate now. So how that turning effect happen? According to Fleming's left hand rule. And another rule is called Fleming's right hand rule, my dears. Fleming's right hand rule. Hand rule, which is for generating of your generators. So motors are working based on the Fleming's left hand rule. Generators are working on the basis of Fleming's right hand rule. Same thing but in right hand. The forefinger represents the direction of the force and the middle finger represents the current direction, and this will be the direction of the what? Lines of force or flux line bus. Okay. Then that means in generator action, what are the things we have? We have the rotation, we have the magnetic field direction, then we are taking, or due to the result of these two, there will be a current flow. That current will be mutually perpendicular direction. Is it clear? Is it clear? So this is the Fleming's right hand rule and this is for Fleming's left hand rule. Fleming's right hand rule is for generator. For remember this in our lectures and all, no, when we taking classes, when I took class for juniors, I mean for students, what the example I used to remember this generator action and motor action for Fleming's left and right now. So generation means you have to generate energy now. You have to generate energy so that you have to take your meal and using your right hand you have to take it to your mouth. Correct? You have to take your meal and you have to bring up to your mouth and you have to swallow. Then only energy will be generated, no? So the generator action will be based on the Fleming's right hand rule. But by using right hand we are eating, no? That's simple. That is the simple example we normally use to remember always that motoring, I mean left hand and right hand, because it is confusing, no? Quite confusing. So sometimes it may be interchanged. We don't know what is actually. So at that time you can use like this. Generator means something we have to eat and generate energy. So by using your right hand you are going to eat and you are generating energy. So Fleming's right hand rule is for generator action and Fleming's left hand rule is for opposite, simply for motor action. That's all. Okay. So that's all about for DC motor, and now we are going to see DC motor application. DC motor applications. DC motor application. Applications of DC. First of all, we have to see shunt motors. Shunt motor. Shunt motor. See, shunt motors are what? Normally constant speed motor. I already told you that shunt motors are normally constant speed motor. So shunt motors are used where constant speed, you need a constant speed in some application. So what are the applications where you need constant speed? Means lathes and drillers, shapers and boring and spinning and weaving machines. Spinning and weaving machines. So lathe, driller, shapers, boring, spinning and weaving machine. Where you need a constant speed, you can use shunt motor. Constant speed in the sense, no, you can adjust the speed and again it will come to the constant speed, that new speed, and it will continuously operate in new constant speed. You can adjust the speed. Suppose it is 500 rpm is one speed, you can change it to 1000 rpm also, then it will continuously operate in 1000 rpm. No? Because lathes and drillers, no, you have various speed and you can directly control the speed and you will get another speed and it will continuously operate in the other speed also. Okay, constant speed in the sense not always on 1500 rpm, no, it can change the speed and it will remain continuously the new speed, that's all. So that's all for the shunt motor application. Next is series motor. Series motor, you just remember this name, bas. Okay, series motor is actually a variable speed motor, my dear. I already told you, series motor is called the variable speed motor. No, initially it have some torque, and torque is very, you can rapidly changing the torque. Okay, the torque is very much influenced by the armature current. So it is a variable speed motor. So whenever we need the variable speed application, you can use the series of motors. So the applications are, I already told you, traction and elevators. Tractions and elevator, where you need why we are using this in traction and elevator mean not only for the variable speed, but also we are using it due to high starting torque. These two application is due to high starting torque. Here also the variable speed in the sense, it is not, you can vary the speed, but it need not be vary all the time. You can vary the speed and fix to some other speed and it will continuously operate like a shunt motor. But the speed can be very much you can vary the speed. That is the meaning of variable speed. Okay. And why this traction and elevators are very much important? Because in examination and all, these two examples are normally asked. Traction and elevators means due to its high starting torque. Traction means something, traction purpose, train is a traction purpose, So suppose the train is in rust, the passengers are inside, so it will have a very high inertia. It now have a very high inertia. So by overcoming that very high inertia, you need a very high starting torque. That is the reason why we are using series motors there. And in elevators, escalators or elevators, you already know this. So there also, suppose so many persons are there or so many load is there, and it has to start from by overcoming the very high inertia. So you need a very high starting torque. So whenever you need a very high starting torque, there you can use what my dear? There you can use our series motor. Okay. And next, compound motor. So compound motors are actually, see, differential compound motors and cumulative compound motor. Differentially compound motor. they are rarely used, my dear. Rarely used due to its poor torque slip character. Correct? Not slip, my dear. Due to its poor speed torque or speed regulation or poor speed torque character. Okay? And the other is cumulatively compound motor. Cumulatively compound motors, which are constant speed motors. Which are constant speed motors and used where irregular speed change happens. It's a constant speed motor, but used where irregularly what speed is changing. No? That means for some time it is operated in 1500 rpm. For other sometime it is operated in 1200 rpm. For other sometime it is operated in 1250 rpm. No? It is constant speed actually, but there is a chance of speed changes continuously, and it will continuously operate like shunt machine. It is used. So where its application is, where are this application? Presses and shear and reciprocating machines. So these are the places where we can use our cumulatively compound motor. It's a constant speed motor. You can use here for very variable speed condition, and that speed is also constant in nature for some more time. Okay, that's all. So presses, shear means nothing but shearing force. What do you mean by shear? Is suppose this is my book. Suppose I am applying some force like this. This is called the shearing force, my dear. So there are some shearers. You can use some shearers. In many applications are there. Shearers you are using. So at that time you can use what? Our compound motor. So presses, this presses, and reciprocating machine, that also you know. So now I need to explain. So these are the applications. Next, speed control of DC motor. Speed control of DC motor. Listen, my dear. We have the relationship as n proportional to EB by 5, or I can say like n proportional to EB is what, my dear? V minus I into R divided by 5. Am I correct? V minus I into R divided by 5, where R is equal to RA plus RSC for series motor, and which is equal to simply RA for shunt motor. That's all. So generally n proportional to V minus IR divided by 5. So there are two important methods you can use for controlling the speed of a DC motor. First is called by controlling the flux, is called flux control method. And second is called by controlling armature resistance, or simply resistance control method. Resistance control method. Okay, so now we are going to see series motor speed control method. Okay, series motor speed control method first. series motor speed control method. Thirds. Because shunt motor na, it's type a constant speed motor na, so we are giving more important to the series motor speed control. Okay, so first of all, field diverter, by using field diverter, by using field diverters. Okay, draw the figure. See, this is the circuit diagram for, by using field diverters you can vary the speed of a DC series motor. How? See, we have the basic equation as n proportional to 1 by 5, am I correct? So you can directly vary the flux in order to control the speed, okay, in order to control the speed. So is a type of flux control method actually. So what we are going to do is, you are inserting a resistance in parallel with the series field winding. A resistance in parallel with the series field winding. What happened then? See, this is the incoming current, my dear. This is the incoming current. The motor is running at some value. Suppose the motor is running at 1500 RPM. You assume. Before inserting this, the motor is running at 1500 RPM. Okay. So I am inserting this what a resistor, rheostat. This is called the field rheostat. So I am inserting this rheostat in parallel with the what series field winding. What happens? What happened, my dears? There is the total current is not changing now, but what happened? There a portion of the current will be flowing to this resistor. That means the current through this will be reduced. Correct? The current through this will be reduced because a portion will be flowing through the upper resistor side. That means because it is in parallel, so it having some resistance value, so it will absorb certain amount of current. It will absorb certain amount of current. And what happens then? So it will absorb a current which is smaller than the previous value, correct? Now the current flowing through this series field winding is lower than the previous value. That means the phi will be reduced. The phi will be reduced. When the phi reduces, the n will be increases. N will increase. So this method of speed control is used for control speed above rated speed. Am I correct? Because this we can't reduce speed below normal speed. That is 1000. Suppose it is 1500 RPM. Then only way to reduce the speed in order to increase the phi. We are not doing to increase the phi here. Anyhow, you are inserting some resistance, means there will be of course some decrease in the field current, and of course there will be a increase in speed, not decrease in speed. It's very, very important. So by using field diverter, we are using a field control, I mean speed control in such a manner that we have to only what? Increase the speed above the rated speed, not for decreasing the speed. And second method is also there, my dears. Second method. Okay, easy. You note this. And second method. Second method. Or it will be B. That is armature diverter. Armature diverter. See. See what happened here in armature diverters. So suppose now the motor is, before connecting this diverter, the motor is running at 1500 rpm. You assume, okay, 1500 rpm it is running. Suppose I insert something in parallel. What happened? What happened? What happened, my dears? The happening thing is that now this current through this series field winding is okay. It is continuously flowing. It is continuously flowing, and the effective resistance now, it is decreasing now. That means by adjusting the resistance value, we can control the current, that is IA. So something is connected in parallel with the armature means the effective armature resistance will be reduced, correct? Something which is parallel with this armature means the effective armature resistance will be what? Reduced, correct? The effective armature resistance will be reduced. Am I correct? So what happened? If the effective armature resistance is reduced, the current will be increased, correct? The current will be increased. Compare with the previous thing, there you inserted something here. So the current is here. It field again the same armature resistance here. Here you can adjust the field resistance. I already told you, series field resistance is always low, very low. Even if you add something in that low value, that value doesn't change much. Compared to the armature resistance, the series field winding resistance is very low. But if you add something in parallel with the armature, the effective armature resistance will be reduced so that the current will be very high. That means this incoming current, this will be very high. If the incoming current high means the flux here also very high. If the flux here also very high means we have the relation N proportional 1 by phi. If phi is high means N will be reduced. So you can control by using this method, by using this method, you can control speed below rated value. You can control speed below rated value. Okay, so that are the two speed control mechanism of DC series motor. Okay, DC series motor. Is it clear? Is it clear? Okay, can I rub this? Next, so that's all about DC motor, and next we are going to deal with single phase induction motors. Single phase induction motor. See, you already learned about the three-phase induction motor, and you know the working of that three-phase induction motor, how it's work and all. The peculiarity or the speciality of the single-phase induction motor is that it's not self-starting. Because there is no rotating magnetic field. There is no rotating magnetic field. How can it happen? I will explain. Consider this is my stator winding, stator, and not need to use brushing down. You can directly give single phase supply. So phase and neutral will be there. So there will be stator winding. Okay. there will be stator winding. So of course in certain region, suppose you want for 2 pole, then suppose this region contain a current which is moving into the coil, and this will contain current moving outside from the coil. Suppose you want it for a 2-pole structure, what happen? You can want for any poles, no issue. Suppose you want for 2-pole structure, this region, this half will contain current in the inside manner, and this portion will contain a current in the outside manner, and inside which there is the rotor, which rotor is nothing but in squirrel gauge rotor. Rotor is nothing but squirrel gauge rotor. Squirrel gauge rotor, and this is stator and wound for single phase. So what happened? The nature of the magnetic field produced here. See here what happened, my dear. Here the current is moving into the coil, so the magnetic field will be clockwise. By using right hand thumb rule, the magnetic field will be clockwise. So there effectively a clockwise magnetic field. Here also effectively a clockwise magnetic field. Here also effectively a clockwise. Here also effectively a clockwise. Here also effectively clockwise. So effectively a clockwise magnetic field will be arised here. So I can draw like this. So effectively there will be a clockwise magnetic field. The opposite will happen here. So effectively there will be a what, my dear? Anti-clockwise magnetic field. So by observing this diagram, this portion will be act as the south pole, and this portion will be act as the north pole, because inside the magnet what is happening, my dears? This is this now. So inside the magnet, so this will be the flux line, and this will be the flux will move from south pole to north pole, and external to the magnet it will from north pole to south. Okay, so this region will act as the south, and this will act as the north. This will be there for what? Suppose this is south and this is for positive half cycle, my dear. This is for positive half cycle. In the negative half cycle of the AC supply, what happened? The things will be reversed. That means here will be the same thing will happen here. So here will be what? Anti-clockwise, and there will be a clockwise. That means the polarity here now, so suppose this will be in dot, this all will be in dot, this all will be in clock for next half cycle. What happened? The current will be moving outward, the flux will be like this, so there will be the flux in upward direction, so that this will be south and this will be north. Bus. No change in that. The continuously this is happen because we are applying 50 Hertz supply, my dears. We are applying 50 Hertz supply. So continuously this north south pulse is simply what? Changing, not turning. It is simply changing. Whenever we deal with what? 3-phase induction motor, there was a flux of magnitude 1.5 into 5m was continuously rotating 60 degree. Whenever we are moving 60 degree, the magnetic field also moving with 60 degree with same 1.55m, same 1.55m. It will cover complete rotation whenever we are applying a complete AC cycle. When the AC cycle completes, what happened? The flux also completes 360 degree. But here there is no rotational effect. My dear. So in 3-phase induction motor, the reason for the rotor to come to rotation, what was that? Rotor is stationary. Suppose I am the rotor, I am stationary. Someone is rotating around me with some synchronous speed. So I am looking that, okay. That was the reason why some flexes on me and I am start rotating. But here, the rotor itself have some inertia. So this south, this north, this south is continuously varying and fluctuating. That is called the pulsating torque. So due to this pulsation, what happened? The rotor is really confused. Which direction I have to start my travel, or which direction I have to rotate? The rotor got confused because that's much speed now. It is continuously changing. So the rotor didn't get enough time to think in which direction I have to move. See, when I'm looking for something, it is south. When other time it is north. It is other time it is south. It is other time it is north. Where I have to go? Where I have to go? The rotor will be confused. So the rotor will not start at anymore. The rotor will be simply in standstill condition, because there is only a pulsating torque, not a rotating torque. Rotating torque, not a rotating torque, my dear. It is simply a pulsating torque will happen there, not a rotating torque there. Even if you make a stator like 4 pole, 6 pole, 8 pole, 16 pole also, there will be simply north and south, simply changing, pulsating, not rotating. For rotational magnetic field, at least you need 2 waves, my dear. 2 waves you need. Then only there will be a rotation. There will be 2 waves which are lag or lead between them by some angles. Then only there will be a rotational effect of flux will happen. That's happened already in the 3-phase induction motor. But in the case of single-phase induction motor, since we are applying a single supply, my dears, there is nothing to compare with. So there will not be any rotational effect of flux, resultant flux happen. So what happened? There will not be any rotating magnetic field. The motor will not start it anymore. The rotor will be simply standstill condition, or simply it will remain for rest. It will remain for rest. So how can we start the induction motor? Anyhow, we have to start now. Our fan and all, we are using single phase induction motor now. So we have to use single phase induction motor many situations. So how can we start the single phase induction motor? How can we start the single phase induction motor? There you need a separate winding, which is I will explain now. So did you get the idea? Did you get the idea why the single phase induction motor is not self-starting? Did you get idea, my dear? Did you get the idea? Okay. So for removing that, we are using capacitor starter motor. Let's take an example of capacitor starter motor. Capacitor starter motor. So the single phase induction motor are simply not self-starting. That is a very important point you have to note. Let's see how can it be started. How can it be started? By using a capacitor starter motor, we can take the explanation as an example. Okay, see, this is nothing but the rotor. So this is MW is called the main winding, and AW is called the auxiliary winding. So this is called a centrifugal switch, my dear, which is nothing but which acted according to the centrifugal action. That's all. Simply switch you can remember like. So this is the rotor. This normally squirrel cage rotor. How can it be operated? Let's see. So initially the centrifugal switch will be in closed position, so that the capacitor will be included and auxiliary winding will be also included. Due to the presence of this capacitor, my dears, what happened? There is a phase difference between the current through this, let it be called auxiliary current, and this is called main winding current IM. So there will be 2 currents occurred, and these currents will have some phase angle because of the presence of capacitor. Because the presence of capacitor will leads always leading the current by some angle. So this Ia will lead more than this Im. That means in the waveform, suppose this is the Ia waveform, this is Ia waveform, the Im waveform will be simply lag by some angle. This is called the Im waveform, main winding waveform. So there is something, a relative what? Relative speed or relative motion between these two currents or these two waveforms. So there will be a rotating magnetic field. And when the motor or the rotor, what happened? There will be a rotating magnetic field. So the rotor starts rotating. Whenever there is a rotational effect of magnetic field around its periphery of the rotor starts rotating. Because now you want two waves. Suppose you have two waves, then there will be some resultant wave. When the two waves propagate, the resultant also propagate, my dear. That's all. Okay. If you have two waves, there will be some resultant. When the two wave propagates, the resultant also propagates. The resultant also rotates. That's all. So the resultant will rotate like a rotating magnetic field, and the rotor will be what? Simply start like a three-phase induction motor. It will rotate, start rotation. And what happens when the motor reaches 70 to 80% of normal speed or rated speed? Normal speed. What happened? This centrifugal switch is closed. Opened. This centrifugal switch got opened, and what happened? This oscillating winding is detached from the supply. Now the motor is running with some speed, overcoming all the inertia. Suppose even if you change the polarity like north-south, pulsating manner, it can catch up. See, initially it was in inertia, so north-south continuously changing. It can't respond. Now it is rotating in some speed. So even if it changes north-south, it can catch up to that north, that south easily. It can catch up. Even though it's pulsating, it can catch up. That is the thing. So the rotor will continuously rotate. Okay? And I will give a beautiful example. In your home, when you buy a new fan. Fan is a single phase induction motor. Our fan is a single phase induction motor. So what happened? It is exactly capacitor start and capacitor run motor. Exact word for single phase induction motor, it is that. So when you buy a new fan, the full speed of the motor will be very high. You will be astonished, oh, what a super fan I have, worth for money, no? After 1 year, what happened? Even if you adjust to full speed, it won't. Even if you adjust for 3 or 4, it won't give enough air. The speed will be continuously slowly deteriorate, or the speed will be diminished. You can't get the original speed when you bought the fan. Full speed means it is directly into the supply, then also the speed will be reduced. So for overcoming that, the electrician will inspect our home and will say, "Arey sir, the capacitor of the motor, the fan got gone. We have to buy a new capacitor." So by spending 30 or 40 rupees, you will buy a new capacitor and you will connect. It will continuously rotate like before. It will move in a full speed manner like before, and you are happy. Why? So by slowly, but when years passes, the capacitor, see, it is actually we are using electrolytic capacitor here. Capacitor here. It is slowly deteriorate, my dears. It is slowly deteriorate. Deteriorates under the capacitance value. It can't store. It won't provide much leading than before. So what happened? There will not be a super powerful rotating magnetic field. A super rotating magnetic field will not be there. A very, very bad rotating magnetic field will be there, so that the motor won't catch up to that much speed. Is it clear? So how can we overcome that? Suppose and whenever years more, suppose 2-3 years more passes, what happens? When you switch on your fan, the fan won't work. Its capacitor permanently damaged. So at that time, there is a way to rotate that. You take a stick and try to move the fan in some, suppose the fan is all fans are moves in anti-clockwise direction. You have to rotate in anti-clockwise direction, and it pick up some speed. You switch on, it will catch up. It will catch up because that 70 to 80% of the speed normally provided by this auxiliary winding, that speed provided by us now. But every time you can't run now. So that's why we have to simply replace the capacitor, and it will work like as smooth as before. Is it clear, my dears? So that is the concept of capacitor starter motor. So by using this an auxiliary winding, you can start the single phase induction motor as 3-phase induction motor, and after reaching 70 to 80% of the normal speed, every induction motor is working like this. We have to initially we have to pull that motor to some rated value, some rated speed. After that you can simply exit that way. That way means you can exit from this auxiliary winding. It will continuously rotate by using the main winding. So main winding, the name main winding means it will be continuously operating for a long time. It is always with the motor, but this is just for some time. This is just for some time. No? Okay, is it clear, my dears? Is it clear? Next, equivalent circuit of 3-phase single phase induction motor. Draw this, my dears. Draw this. Standstill equivalent circuit and running condition equivalent circuit. Draw this and I will explain. Draw this and I will explain. Yes. Is it clearly visible, my dears? It's clearly visible. No issues. Okay. See, this is the equivalent circuit of a single phase induction motor. I already told you that single phase induction motor can be viewed like a transformer, single phase transformer, right? So there will be a primary winding, like here it is stator winding. So R1 and JX1 are the stator winding, and there will be a magnetic field, shunt field, shunt R omega or RW JXM parallel path in a shunt parallel path in primary. So RW we can very negligible, so it can avoid this, but JXM will be there because this is the reason for the magnetic field setup. So JXM will be always there, and this is called the rotor resistance and rotor reactance bus. So this is a general simple circuit diagram. Suppose you can see why the single phase induction motor is not self-starting. These can be viewed, or these can be explained with the help of a theory, famous theory called double revolving field theory. So according to this double revolving field theory, why the induction motor is not self-starting means, at the time of starting the single phase induction motor, there are two fields generated inside the motor. One will be rotating in clockwise direction with a slip of S, and other will be rotated in anti-clockwise direction with a slip of 2 minus S, and both are equally and opposite magnitude torques. So what happened? This equal and opposite magnitude rotating torques it will cancel each other. So these and these torques are equal, so that it will cancel each other. So the net effect will be there is no rotation. So double revolving field theory gives the explanation as why the motor is not starting. Why the motor is not starting means there is no resultant torque inside the motor. There is no resultant torque means there is something moving like this, and opposite direction there is also something. So this is the explanation for the no rotation of single phase induction motor, and the detailed explanation is now. See, my dear, so the stator side you can't touch, it is simply R1 and JX1. Okay, the rotor JXM, it can be split by JXM by 2 and JXM by 2. Because it's connected in series, it will simply JXM. Okay, no doubt in there. And the rotor side I am going to arrange in certain manner. R2 dash is nothing but rotor side. I mean, suppose you take the rotor into the stator side, then the equivalent resistance of the rotor is called the rotor resistance, R2 dash. Okay, so this simple R2 dash can be split by R2 dash by 2 and R2 dash by 2. Is it clear? Under standstill condition. So under standstill condition means, my dear, slip is equal to what? 1. Under standstill condition means slip is equal to 1. It's very difficult to understand. Okay, so please listen. It is actually a beyond level imagination. So if you really have a good imagination skill, then only it will be clearly but pictured to you, otherwise it will be very difficult. Okay, listen my dears. So what happened, so under standstill condition slip is equal to 1, so r2 dash by 2, this r2 dash by 2 combined together simply r2 dash, okay, there is no change. Other one x2 dash by 2 and x2 dash by 2 simply combined together by x2. So this and this will be same. Is it any doubt there? These and these will be same. Is it any doubt? No, these are same. Okay, you correctly found out. This is under what? Standstill condition. So this flux now, this session is called the forward field flux, and the torque developed due to this is called the forward torque, and this is called the backward field flux, and the torque developed due to this is called the backward torque. Under running condition, what happens, my dear? Under running condition, there will be some slip now. There will be some slip. So these flux and these flux are the same. This resistance and this resistance are same. This reactant, the similar. This is exactly a replica of this now. So the flux produced by this will cancel the flux produced by that. So there will not be any starting effect. So the machine won't start. That means the applied voltage will be utilized for generating the forward EMF plus the backward EMF, EF plus EB. So V will be equal to EF plus EB, and both start rotating in different direction, opposite direction with equal magnitude. There will not be any flux at all. I mean the resultant torque. Okay. Under running condition, my dears. So under running condition means there will be some slip. There will be some slip. So the forward field flux can be treated like, see, Jxm by 2, there is no change in R2 dash by 2s, my dear, and Jx2 dash by s. Okay, and the backward field flux can be treated like Jxm by 2 and this R2 dash by 2 into 2 minus s. You have a confusion. Why, sir, you take R2 dash by 2s in one and 2 into 2 minus s in other? Is that same equal to this? Yes. Put s is equal to 1 there. Put s is equal to 1 there. What will be? R2 dash by 2. Same na, R2 dash by 2. Put s equal to 1 here. R2 dash by 2 into 2 minus 1. It is 1. So R2 dash by 2. R2 dash by 2 na. So there is no change. I can represent the same diagram, my dears, in this manner also, in that manner also. Is it clear? So these diagram and these diagram is same. This is for standstill and this is for running. That is the only difference. So you can observe two things here. First one, the forward flux and backward flux are not equal now. This is equal to this. Okay, I agree. But under running condition, now my dears, under running condition, the slip is not 1. The slip, suppose you take slip is equal to 0.5. So R2 dash by 2 into 0.5. Here R2 dash by 2 into 2 minus 0.5 is 1.5. So the forward flux and backward flux will not be same here. So there will be a rotational effect. If something here and something here, if it is exactly balanced means it won't rotate, my dears. But if something is higher than this one, it will definitely rotate. So motor will rotate now. That is the reason why the rotation happens. But this is just an equivalent circuit. But our work is what? Actually our headache is what? In order to make it rotating. After rotating, you can simply draw the equivalent circuit and all. You can explain, but you have to make it rotation is the real task. Okay, so this is the equivalent circuit. So this is called the forward field flux and this is called the backward field. So I already told you one thing. Under running condition, due to double revolving field theory, this is the double revolving field theory, my dear, simple bus. So final conclusion is what? The rotor is in rotation condition or rotational. At that time of rotation, what happened? There are two slip, my dear. One is called the forward slip. There is a relationship of that forward slip. Let it be. Okay, I'm going to rub this. There are two slips, my dear. One is called the forward slip which is equal to simply S, then backward slip will be equal to 2 minus S. And there is a relationship called forward slip let be SF and backward slip will be SP equal to 2. This satisfies the relationship. See, R2 dash by 2 into S means the S slip is S. R2 dash by 2 into 2 minus S means the S will S in at the place of this S, here it is 2 minus S. So the slip will be 2 minus S. In examination there was one question, I have attended that question and I still remember that question. Okay, that means in some induction motor, single phase induction motor, what is the slip of the, or what is the backward slip? Directly you ask, the questionnaire were asked the backward slip. So S is the forward slip, means 2 minus S will be the backward slip. Minus 2 minus S will be the backward slip. Okay. Okay. Okay, or 2 minus forward slip will be the backward slip parts also. Okay. Substitute this forward slip but backward slip will be equal to 2 now. Satisfied? Say okay. That's all. So that's all for the concept of rotating magnetic field. So in the single phase induction motor, there will be 2 slips happens. I mean 2 torques happen because 2 slips will be there. Definitely 2 will be. One is forward direction and other one is the backward direction. So forward directing slip will be S, backward direction slip will be 2 minus S, my dear, 2 minus S. Okay, so that's all for today. Let's meet with a new topic on tomorrow. So until then, bye.